So welcome back to BIOM-MECH 543. This is going to be Unit 4. In Unit 3 we talked about fouling and different membrane applications, why fouling is important, why it's very important to try to alleviate fouling, and the different mechanisms of fouling and how to combat that. We ended up with talking about gas permeation, I believe, gas separations, and the two different ways to do that. One is permeation separation, another one is something called pervaporation, and I'll talk about why the differences there and why each one might be used. The transport through these membranes, these non-porous membranes, is diffusive mediated. So there's no true pores in there, so we can't get a true convective flow. We can't get the liquid pushing the stuff through. So the main transport is just the diffusion rate of the gas molecules through these dense membranes. Another dense membrane that might not be so apparent is actually the dialysis membrane. Because of the types of solutes that you're trying to separate out are very, very small, on the molecular order. So we can't have true pores because they would just let everything through. So these are also very, very thin, dense membranes as well. Dialysis is different than the filtration mechanisms we talked about before, which is a pressure-driven force. Dialysis is actually a concentration-driven force. So you have your toxins that are built up on one side. The bag will let those toxins flow through while retaining the water and stuff on the other side. And it's basically, it's designed to act like your kidneys to produce, I call it fake urine, but it's urine, basically. So different uric acids and water-soluble impurities. So concentration-driven force, not a pressure-driven force. We'll also talk about here a little bit with carrier-mediated transports. This is trying to mimic closer to a biological membrane. So there's certain molecules we can put in a membrane that will specifically bind to, certain solute molecules on the bulk side and help transport them across the membrane either faster or at a higher concentration than other ones. And that's a type of separation as well. That's a type of active transport. We can talk about electrodialysis, where the driving force is actually an electrical gradient, some sort of voltage gradient. So you'd obviously have to be working with some sort of charged or non-charged particles. We'll talk a little bit about membrane contactors. And what that basically means is the membrane serves as a separation of two bulk phases. They can be liquids, they can be liquid gas, or it can be gas-gas. But you don't want those emulsing or coming together. So that serves as a barrier and lets certain things through. Blood oxygenators are a great example of that. You don't want all the gas going to the blood, all the air, because gas bubbles are very detrimental. But you want oxygen transport at a controlled rate. And at the end, we're going to start to move away from that and talk about a totally different topic, where to date we've talked about kind of the current methods, what's already been done with membranes. We're going to talk about kind of emerging membrane preparation methods. So this is talking about the true research going on right now. We'll talk about the current research topics in terms of membrane materials, which is a big one. So that's a lot of the polymer chemists, materials engineers, whatever, they're working on that. And also we'll start to talk about modifying those materials after they're made to make them more readily better for whatever application we're looking for.